So this is a benzene molecule first. I think this is going to be my best attempt, and okay, yeah, it is. So yeah, we've got a benzene molecule, and then we've got a phenol. For phenol we have OH attached to this. This is phenol. Now, phenol is insoluble. Why is it phenol? Why is phenol insoluble? So you must be wondering that we have OH over here, and this oxygen atom has two lone pairs, so it can form hydrogen bonds with water molecules. Well, the thing is that this benzene molecule is so big compared to this phenol group that it disrupts the hydrogen bonding. It disrupts the hydrogen bonding between the phenol molecules and water molecules. So the benzene molecule disrupts the hydrogen bonding because it is so big compared to the OH group. So it disrupts the hydrogen bonding, and therefore phenol is insoluble in water. Disrupts the H bonding, disrupts hydrogen bonding, and because the size of benzene is greater than the size of this OH group, so it disrupts the hydrogen bonding between this OH group and water molecules. So phenol is insoluble in water. Phenol is weakly acidic. So what happens is that if I write the structural formula of phenol, which is C6H5OH, so this can form an acid. Now it can form C6H5O plus, C6H5O negative, not plus, it will be C6O5H5O negative, which is the phenoxide ion, and H plus ions. So you know the definition of an acid is that an acid is a proton donor. The Bronsted-Lowry definition of an acid is that an acid is a proton donor. So since it has released a proton and formed a phenoxide ion itself, it can be called an acid. This reversible reaction sign tells us that it is weakly acidic, so it dissociates into ions partially, but it is weakly acidic. It does behave as an acid, and we'll be talking about this further right now. But you need to know that this this does behave as an acid because what happens is that, as I told you before, the lone pair on the OH atom on the O atom delocalizes into the benzene ring. So as it delocalizes into the benzene ring, it is no longer available to accept H plus ions. So as it cannot accept H plus ions, it acts as an acid, because an acid donates H plus ions, does not accept them. So the lack of the availability of the lone pairs results in the oxygen not accepting H plus ions and hence behaving as an acid. So phenol is weakly acidic, and phenol is a lot more reactive than benzene. Now, why is phenol more reactive than benzene? I have already told you. If you pause the video and think of it, the answer is right on your screen. If you look at this diagram carefully, the answer is right on your screen, and you'll understand why phenol is much more reactive than benzene. So pause the video, think about it for a minute, and play again. I'm sorry. Phenol is more reactive than benzene because as the lone pairs on the oxygen atom delocalize into the benzene ring, the negative charge density on the ring is greater, and since the negative charge is greater, the 2, 4 and 6 groups are activated, and these groups are activated, which means that because they have more negative charge density, so they will react much more readily than normal benzene. And we will learn what this has as a consequence on the conditions used in the reactions with phenol as we go further. But As these 2, 4, and 6 positions are activated, we have this molecule becomes much more reactive.